Alright guys, welcome back. Today we're going to talk about geometric proof. So after looking at all those circle theorems, we are finally going to think about how to prove them. It's just like a lot of the times in our life and throughout history, we know how to deal with stuff before actually even wondering why they are the case. Right? So in these two lessons, we are going to explore proving some of the theorems, including some of the circle theorems that we looked at in the past few weeks. So let's start with the first example. This is actually to prove the semicircle theorem, the very first circle theorem that we encounter in this unit. We are going to prove that if you are given a semicircle, that means if your AOB is actually 180 degrees, okay? Meaning that in this case we are actually crossing the center O with a 180 degree flat line, okay? And if we have that, we will be able to prove that the APB in this case is equal to 90 degrees. So at the end, our goal is to prove that this APB has to be equal to 90 degrees, right? So we know this theorem, but the problem is how. Like, why is that? Why does the fact that we have 180 degrees there be able to guarantee that we have 90 degrees there? Okay, so we're gonna go through some steps. Now, the first step that I will claim is the fact that all those OP, OA, and OB are the same because those are what we call the radius. Okay, so the reason behind that, we put a reason at the end, is that the fact that we have radius for all of them. And then you'll realize, just because we have the radius, we will be able to form two isosceles triangles. One is this POA, the other one is this POB. So first of all, you will say angle OPA is equal to angle OAP. Okay, we're basically talking about these two angles being the same. And then, similarly, we can also say OPB equals to OBP. So we're talking about these two being the same. Okay, for both of them, the reason is the same. Okay, we have isosceles triangles. Just for convenience, we will call alpha APB. And since APB is equal to ABP, right, so both of them are alpha. And then we will call the other two pairs beta, namely OPA and OAP. And then you realize that if you add up all those alpha, alpha, beta, beta, we're actually adding all the three angles in a triangle. It doesn't really matter what kind of triangle it is, but we at least know that it's a triangle, and it should add up to 180 degrees. So now we have alpha plus beta equals to 180 degrees. And the reason is because we have all angles in the triangle adding up to 180 degrees. And then you factor out the two. We have a plus b inside, and that's equal to 180 degrees. And we are basically done, because in this case, we're basically proving that a plus b, alpha plus beta, right, alpha plus beta is equal to 180 divided by 2. That basically says this whole thing over here is actually 90 degrees. And what is that whole thing? That is exactly what we were trying to prove at the beginning, APB. Okay, APB is equal to alpha plus beta, and according to our algebra, we can prove that this is actually equal to 90 degrees. And you put a little box at the end to kind of tell people that you're done proving, and that's the end of the proof. So from the previous example, you can kind of see the format. Okay, it's not always exactly the same, right? You don't have to be so self-conscious about, being able to follow exactly what the framework. Okay, sometimes it might be a little bit different, but here's the structure basically. So you'll start with some statement that you're trying to claim something. For example, in the previous example at the very beginning, I'm claiming that I'm having OP equals OA equals OB. So that's my first claim. And then you see that I'm giving a reason in the square bracket. Okay, and then usually followed by that claim, you will be able to have some other statements as a result. So for example, in this line over here, right, I'm having another result over here. Sometimes you may or may not, have another reason followed by that, okay? And then you probably will have another statement, and then you'll have maybe some other statements as a result. And then once you finish collecting all the evidence, you put them together and you put your final claim. In this case, my final claim is this equals to 90 degrees, and which is exactly what we're trying to prove. And if you can get to there, that means you're done with your proof. So basically, this is the format that we'll be following for our proving in the next following days. So let's look at another one. We're given that TC is a tangent, right? So here we have a tangent. Our goal is to try to prove that we have this AC line that will cut an angle called BCT into two equal pieces. So we have this angle over here. This statement is claiming that we should be able to cut that into two equal pieces. We're going to find out whether that's true or not. So we're not going to mark the crosses yet, because we don't know whether they're exactly the same until we prove them. Now the first thing is, you will probably realize that ABC is equal to ACT. Okay, we're talking about the fact that this angle is the same as this angle over here. Remember, this is our very famous tangent chord theorem, so you can put the reason after that. This is a tangent chord theorem, okay, right? Because this is an inscribed angle facing this arc, and this arc got eaten away by this angle, so they're the same. And then, on the other hand, you can also see that ABC is actually the same as ACB. So we're talking about the fact that these two are the same. Right? Why are they the same? Is because we have the isosceles triangle. Right? These two sides are the same. That means we have isosceles triangles. If you have isosceles triangles, that means that we have these two angles being the same. So ABC is equal to ACT. ABC is also equal to ACB. That basically means our ACT is exactly the same as ACB then. Right, so basically we're saying that this ACB is exactly the same as ACT. And that's exactly what we want on the fact that AC is bisecting the whole BCT. And therefore, we just need to do our final claim. Therefore, AC really does bisect BCT. And that's the end of the proof. Last example of the day. So we have been looking at this tangent chord theorem many times already. We even saw that in the last example. The whole name is called angle between a tangent and a chord theorem. So in this question, we're going to actually prove them. So let's follow the steps over here, step by step, and eventually we'll be able to prove them. So part A, we have a little part 1 over here, and then part B, a little, so a lot of questions. So let's start with tax, right, TAX, right, what is angle TAX in this case? Right. You'll realize that TAX is actually the same as TAO if you stop here. And this, if you stop here, this is a radius, and then we have a tangent, right? So we can use a tangent radius theorem to prove that the angle is actually 90 degrees, right? So you will say TAX is equal to TAO, which is also equal to 90 degrees. And the reason behind that is because we have tangent radius theorem, and then the fact that our AOX is a straight line. Okay, very good. So that's part 1. Part 2, we want to find the size of ACX. Right, so ACX is over here. And guess what? This is actually 90 degrees. Why? Because do you see that here we have a diameter? Okay, so this angle over here, it reminds me of the semicircle theorem that we proved at the very beginning. So ACX is actually also equal to 90 degrees. Okay, and the reason behind that is because we have semicircle theorem. So that's basically it for part A. Part B, we're going to use what we got from part A to help us with part B. Part B1, CAX is equal to what in this case? CAX is this guy over here highlighted. But then just because you know that the TAX, the whole thing is equal to 90 degrees, and then we are given the fact that the TAC in this case is alpha, right? So you're basically just a leftover. In this case, you have 90 degrees minus alpha. Okay, so that's basically your CAX. Right, highlight that. Part 2, okay, we're going to keep using the previous result. In this case, we're finding CXA. Okay, CXA, which is this guy over here, right? This guy over here. This is basically equal to 180 degrees as the sum of all these angles in the triangle, minus 90, which is the ACX that we found before, and minus bracket 90 degrees minus alpha, which is the highlighted one that we found in part 1. Then you will be able to find your CXA. In this case, if you take out the bracket and then you cancel the 90, 90, and 180, you actually realize that everything can be simplified to just a single alpha. So this whole thing over here is basically just alpha. Let's mark it down. Part 3, we're getting close to the end of the proof. Finally, they want you to find what CBA is. CBA, because if you look at CXA from part 2, this is an inscribed angle that sweeps out the whole arc going from C all the way to A. Okay, we're not using the tangent chord theorem in this case because we are proving that, so we cannot use that now. Okay, but one thing that we can use before is that you will realize that here we also have another inscribed angle called CBA. And these two inscribed angles are facing exactly the same arc over here from C all the way to A. So in this case, you can say that CBA is basically the same as CXA. And just because from part 2, CXA is equal to alpha, CBA is also equal to alpha. The reason behind that is because we're facing the same arc. Okay, we are the same inscribed angles that are facing exactly the same arc. So no matter where you move, as long as you're along the circle, even for this guy over here, I should have alpha as well. So all of them are alpha. So I mark them down. And once we have that, we're basically done, right? So part C, you can state the relationship between TAC and CBA. Okay, remember the actual theorem. The actual theorem is talking about that the angle right here, right, that eats away this arc over here, will be exactly the same as any of the angles that subtends this arc over here. So in this case, we are basically done. TAC is alpha, but then CBA, according to all our proofs over here, we arrived in the conclusion that CBA is also equal to alpha. So in this case, we're just basically going to say TAC is equal to CBA. And that's exactly what the theorem is talking about, so we are done with the proof. And that's it for this question. So that's it for today. I'll see you guys in the next lesson. Peace.